Oak, and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos that I've been posting to the course forum so far, you'll know that I'm going through the SparkFun Inventor's Kit Guide, and I'm showing you how I'm completing the projects and the circuits and associated coding challenges with those projects. So far on the course forum, I have videos showing me completing projects 1 through 4, along with all of the circuits and coding challenges with those projects. Also, my latest video that I posted to the course forum shows me completing Circuit 5A, which is the first circuit in Project 5, and I also complete the coding challenge as well. In today's video, we're going to be going over Circuit 5B and its coding challenge. So if you haven't watched the previous videos, I would highly suggest watching those videos before watching today's, simply because some of the concepts I'm going to be talking about today, I've already went over in greater detail in previous videos, so I won't be going over in as great detail today. However, if you want to watch today's video, by all means, if you do end up having any questions, feel free to refer to some of those past videos. I'll try to mention which ones they are as we go in today's video, or just post your questions to the course forum and I'll be happy to answer. So what are we going to be going over in today's video? Well, this video is going to be guiding you through Circuit 5B from the SparkFun Inventor's Kit, which enables us to control a remote-controlled robot, car in this case, using an Arduino, or specifically the SparkFun RedBoard, which is a generic Arduino board. First, let's take a look at the circuit setup. We're going to have 2 motors for our wheels, controlled by a motor driver connected to our Arduino. The control pins for the right motor are connected to pins 8, 9, and 10, while the left motor uses pins 5, 6, and 7. We've also got a status LED and a switch on pin 2 that we're going to use to turn our robot on and off. The key concepts to understand here involve how we're using PWM, pulse width modulation, for speed control, and how the direction of each motor is controlled through the digital pins. In the Arduino code, during the setup, we initialize the pin modes and begin serial communication, printing instructions for the user to input commands. The main loop continuously checks if the switch is activated. If it is, then we listen for commands sent via the serial monitor, entering directions like forward, backward, left, or right, followed by a distance. Based on the command received, the robot will move accordingly, with the right motor and left motor functions managing the speed and direction using digital rights and PWM. Now let's shift our focus to my coding challenge version, where I've integrated wireless communication using the NRF24L01 Plus module. This part of the project enhances the robot's interactivity. So the transmitter setup sends commands wirelessly utilizing the RF24 library to handle the transmission. I'll demonstrate initializing the radio in transmit mode and processing the serial input. The received commands will trigger the same motor control logic as our initial setup, the setup that's included in the SparkFun Inventor's Kit code for Project 5 Circuit 5B, the code that you can download for free off of their website. This is going to allow us to move the robot based on wireless input from a distance, so we don't have to be tethered to the robot with our computer and a long USB cord. I'll also show how the receiver continuously checks for incoming commands and toggles the state of an onboard LED to indicate when data is being processed. As I walk you through this challenge, I'll explain the logic behind command parsing, wireless initialization, and the seamless motor control functionalities, ensuring a robust understanding of how to manage a remote-controlled robot, both via wired and wireless communications. So wired is using the original code provided by SparkFun, and wireless communication is the code that I'm going to provide for you guys that I wrote as part of the coding challenge. So stay tuned as we run a live demo. I'm going to showcase the NRF24L01 Plus capabilities while reinforcing the underlying principles of Arduino programming and circuit design. So with that being said, let's dive right into the code. So for anyone who's watched the videos that I've done before, you'll know that I go through the SparkFun Inventor's Kit guide, but I don't read everything. I kind of skim over and read the highlights. So that's what I'm going to do today. But if you're new, that's what we're doing. So today we're working on Circuit 5B, a remote-controlled robot. We're basically going to control 2 motors remote control in order to move the robot. So the components that we're going to be dealing with today are the motor driver. We use that in Circuit 5A. 2 gear motors, where we only used 1 gear motor in Circuit 5A, a switch, which we used in 5A, and some jumper wires. So everything's essentially the same as far as components as circuit 5A, if you watch that video, we've just increased the gear motors to 2. And we've also got a couple wheels as well. So, new concepts that we're going to be talking about today's video. ASCII characters, which is the standard for character encoding formalized back in the 1960s. And it assigns numbers to characters. I've talked about this in greater detail in previous videos, so I'm not going to go over it here, but if you have any questions, feel free to post them in the forum. Essentially, ASCII tables are available online. You can follow this link, and that'll just show you the corresponding mapping between the character and a decimal number equivalent, or hexadecimal for that matter. So again, the ASCII tables are available, and they show which character is represented by which number. We're also going to be talking about converting strings to integers. So string variables hold words like dog or Robert Smith and are made up of multiple characters. So strings are actually arrays of characters. And Arduino has a special built-in methods for dealing with string variables, and you can call them by putting a period after the variable name. So this is dot notation. Anyone familiar with programming in high-level languages like C++, Java, Python, all that sort of thing, would be familiar with dot notation, so I won't go over that too much. But essentially, you'd have your string variable, dot, and then your method call, your function. So the toInt method converts a string to a number, so that'll be particularly useful in today's circuit. A lot of the rest of this guide kind of goes over the assembly of how to set up your SparkFun base plate, your plastic base plate and motor, to attach the motors and how they need to be on there and that sort of thing. So I'm not going to go over that. You guys, if you're taking COM 4.4, everyone will have this guide available, or you can get it online from the SparkFun Inventors Kit website. You can just Google that and find it. But once you do have that completed, I guess I'll show you mine quickly. Let me just show you my circuit. So underneath I've got the battery pack, the motors attached with, in my case, 3M command strips, 2 wheels, 2 geared motors, the motor driver that should be familiar to anyone who watched the video for circuit 5A, the switch, and this is for the coding challenge. This is something that won't be included in the PDF I'm about to show you, because this is what I'm using for the coding challenge to communicate wirelessly. So this is an NRF 24L01 Plus module. It's an RF transceiver module, in this case with an external antenna. I also have a version here with an internal antenna. Same module, just has an internal antenna, so not quite as large of a range. That's going to be our receiver, or correction, our transmitter. And this is set up as our receiver, but that's pretty much it. I've also got an LED that I'm using for status purposes. But so that is my circuit setup. But again, some of that isn't included in the basic circuit here, so you don't have to focus on that too much right now. The basic setup looks like this. Again, if you've watched the video for circuit 5A, you'll know it's very similar. The only additional setup really is we have an additional motor hooked up off of channel B, and therefore we're using the B inputs. But actually in the setup schematic for circuit 5A, they already had the wires hooked up for circuit B, channel B, so for the second motor. They just didn't have the output hook up to a motor. So this setup is almost identical to circuit 5A if you watch that video, where we have our motor driver hooked up. We have all of our channel A pins, so for our first motor, with our PWM-A and inputs 1 and 2 hooked up here, and for our channel B, which is our second motor, all hooked up here, and our standby just hooked up to the positive voltage. I'll just increase this here so you guys can see. So just things to note, and this was mentioned in the previous video, our PWM pins for both channel A and channel B do have to be on PWM pins on the Arduino. So our channel A is on pin 11 and channel B is on pin 10. And both of those pins are PWM pins, and you can tell that based on the tilde symbol to the left of the number. So those are your pulse width modulation pins. The other pins can be on any digital pins as they are here. And then our VCC and ground. VCC is the 5-volt logic required for the motor driver. So that just comes from the Arduino. So the 5 volts and ground are hooked to the power rail, which are ultimately tethered to this power rail as well. And so that's where the 5-volt logic is coming in to power the motor driver. However, the voltage for the motors themselves is coming from VM. So for voltage for the motor, and that is tied through the voltage in pin, which would be getting its power from the barrel jack here, which would be hooked to an external battery pack, and that'll be somewhere between 7 and 15 volts. Again, if you remember the battery pack I just showed you on the bottom of my setup, it's 9 volts. I believe it has 6 batteries, 1.5 volts each, for a total 9 volts. And then the outputs here, we have our outputs for channel A for one motor and our outputs for channel B for the other motor. So the only difference really in this setup for circuit 5B is we have this additional negative and positive lead going to an additional motor, a second motor. And then we had the switch as before. The middle pin has to be to ground, and then either of the other pins just have to be tied to any digital pin, in this case 7, same as before. And so what should you see during the circuit? Well, in the original circuit, as shown here, without the wireless capability, you're going to start by flipping the switch to the on position, and then open the serial monitor, and it'll prompt you to enter a command. And then you're just going to type a direction into the serial monitor and move the robot accordingly via the commands. So the original program overview is as follows. Step 1, you prompt the user to enter a command and list the shortcuts for the directions. Then you wait for a serial command, and then you read that serial command and set that as the direction. So if the direction is F, if the user types in a lowercase f, you're going to drive both motors forward. If the user types in a lowercase b, you're going to drive them both backwards. And R, you're going to drive the right motor backward and the left motor forward, because that's how you're going to turn right, by the right motor moving backward while the left moves forward. That's going to give you your best turning radius, so you can turn a lot quicker. And if the direction is L for left, the left motor is going to go backwards and the right motor is going to go forward. So you'll notice whatever direction you're turning in, that wheel is going to go backwards, whereas the opposite wheel of the direction you're turning goes forward, and that gives you a very nice tight turning radius. The code to note during this circuit in this coding challenge, or the regular code for that matter, is parsing strings. So we're going to use the serial.readStringUntil function, and this readStringUntil function takes in any character argument. In this case, we're passing in a space, but that could be anything. You could be reading until a comma or till an F or anything. We're using a space because that's how we're going to input our commands. We're going to input the direction, i.e. F or B or R or L, and then a space, and then the distance we want to travel. So this reads a serial message until the first space and then saves it as a string. So for example, we would read in an F, a B, an R, and L, and that would be our first thing. And then we're going to use the string to in function. So we're going to have our string name, whatever variable we have for our string, and then we're going to use dot notation and call the toIn function. It takes no parameters in, but it converts the string to an integer, provided it can be converted to an integer. So if a number is stored in a string variable, this will convert it to an integer, which can be used in math equations. So you can actually use the string representation of number, convert it to an actual integer so that we can use it appropriately. And then we have some functions here. Right motor, which takes in a parameter, motor distance, and it drives the right motor long enough to travel that specified distance. And then similarly, we have a left motor function that does the same thing, but with a left motor. And then we have the coding challenge. So the coding challenge for this one wasn't really that fun to me. So basically it was create more commands, so add code to the sketch that takes not only the direction but also the distance. The two should be separated by a character. The code can parse out and know where the next value begins. That's kind of just revamping the code that's there. There's not a whole lot difference or anything really interesting to me happening there. So I didn't fully do this. Add more commands, I didn't see that as overly fun either. I mean, that's just adding another if-else statement and some other logic to how you're driving the motor. So I didn't really do that too much either. However, that just would be using different keys to move the robot in different ways. You could do that, or have the commands turn on LED. I did incorporate that. I do have one command where if I send a T by itself, it toggles the LED on, or it changes the state of the LED. So if the LED was off, it'll turn it on. If it was off, it'll turn it on. So T for toggle. So I did do that. But really, I kind of just went a different way with this coding challenge, and I just added wireless capability. So the original circuit has you typing in commands via the computer and then having the robot move, but it has to be tethered via a long USB cord. And I found that very inconvenient, the whole idea of it, and I just didn't like it as much. So what I did for the coding challenge was just add wireless capability via using an NRF24L01 Plus module. And if you've watched any of my previous videos, you'll know that I actually have quite a few videos that add up to a few hours on the NRF24L01 module. And I go through sending text, controlling a servo with a joystick on two separate wirelessly controlled setups. I have bidirectional communication. I have a lot of different things where I basically went through other people's tutorials online, and I've highlighted the pertinent details just to make it a little quicker. So I've went through other tutorials online, and I've just basically highlighted the main features of those tutorials, and then I've come up with some key points associated with the NRF 24L01 Plus modules and put those out. So there is a lot of videos I have on my playlist for COM 444 showing me explaining the NRF 24L01 module in great detail. I'm not going to go into that same detail in this video simply for the fact that I already have that information out there. So if you want more information on that, feel free to post on the forum and I'll send you the links. I'll also include the links to those videos in the video description for this video. But that's essentially what I did for the coding challenge. And then there was some troubleshooting, but we'll talk about that after we get to it. So let's first show some of the code. So I printed out, I do have the code actually on the in the Arduino form, but I thought it'd be easier just to print them out as PDF so I could just look side by side and hover over them without having the Arduino IDE text pop up. So that's what I've done. So I'll quickly kind of show you, before I get to the code actually, I might do something a little different. I did create a little summary to keep me on track, so I might follow this and go back and forth between this and the code. And then we'll do a live demo at the end. So again, I'll kind of read this verbatim to a point. That way I just keep on track, and then I'll try to go back and forth between the code. So the following code involves transmitting and receiving wireless commands using the NRF24L01 Plus modules to control a robot. Complete with detailed Doxygen comments for the NRF24L01 Plus code commands. If you've watched any of my previous videos, you know I'm a big advocate of Doxygen comments. They're basically comments where you add an extra asterisk in your multi-line comment, and then you're able to add these tags like @file, @brief, @author, @details, that sort of thing. @param for the parameters that you're passing in. @return if you have a return type, you can add that. Do I have any return types in here? Maybe a bad example for the return types. But anyway, Doxygen style comments, I'm a huge advocate of them. They're just really, it's a really great feature. By just changing the way you comment your code, a little bit, you're able to then take your code and put it through an external program like Doxygen and create some really nice professional looking HTML pages based on your code. So definitely recommend doing that. Doesn't take much effort and you can get a lot out of it. So, introduction. Welcome to this walkthrough of my wireless robot control project using Arduino and the nRF24L01 Plus modules. In this project, I have a transmitter module that takes user input and sends commands wirelessly to a receiver module, which interprets the commands to control a robot. The transmitter and receiver communicate using the nRF24L01 Plus modules, which are low power and highly effective for short-range wireless communication, which is what we're using them for today. So the transmitter code works as follows. Number one, we do library initialization setup. So first we include the RF24 library. So whenever you're using some novel code in Arduino, some things that aren't necessarily included in the language itself, you'll often have to include a library, whether you're using a servo or the ultrasonic distance sensor, the HC-SR04, or in this case the nRF24L01 RF transceiver modules. You'll have to include a library. Someone's taken the time to consolidate and create a lot of functions and constants and all that sort of stuff, all the code associated with that thing that make it easy to use. So in our case, the RF24 library is what does that. This provides all the functions to interact with the nRF24L01 module. We define the CE chip enable and the CSN, the chip select pins, that connect the module to the Arduino. These pins control the module's operation and SBI communication. So that's the first thing we do. Library initialization setup. And then we're initializing the radio. So I've created an init radio function which initializes the nRF24L01 Plus module. It sets the power level and it opens the communication pipe. So the power level is how much power we want to dedicate from our microcontroller to this receiver. The more power we give it, the larger the range it has. The less power, obviously, the range isn't as big. And we open up the communication pipe. And we configure the module for either transmission or reception mode. And I've got two pieces of code. I have a separate Arduino set up as a transmitter. That's this one. And the nRF24L01 module on my robot car is the receiver. So again, I've got two separate modules. And even though they look slightly different, they're the same module. This just is a smaller, has an internal antenna, and this one has an external antenna. The range on this one's about 100 meters, and this has a theoretical range of about 1 kilometer. So that's that. We're going to have one of them as transmission mode and the other is reception. For transmission, we're going to use the radio.open writing pipe function, which sets the address where data will be sent. The radio.stop listening function ensures the module operates in send-only mode. So you'll notice we have a radio.open writing pipe, which sets the address where data will be sent, and a radio.stop listening function for send-only mode. For the receiver, we're going to have an open reading pipe and a start listening. It'll be the opposite of this. Handling serial input, I've created a method called handle serial input, and that function listens for user input via the serial monitor. So the user will type in commands via the serial monitor on the receiver end. And when a command is received, it uses the radio.write function to transmit that command wirelessly to the receiver. So on the transmitter end, we're going to input commands into the serial monitor, and then using the radio.write function on the transmitter end, we're going to transmit those commands wirelessly to the receiver. So the receiver code, we're going to do the setup, and the receiver code also begins with including the RF24 library and defining the CE and CSN pins. Additionally, it sets up the motors and LEDs because the receiver code is on the actual robot card, so we need to set up the motor and LEDs there. The init radio function initializes the nRF24L01 Plus module in receive mode. It uses radio.open reading pipe, so reading pipe for the receiver mode, not writing like it was for transmit, to configure the address from which the module will listen for incoming data. So not send, it'll listen for incoming data. And then we use the radio.start listening, which activates listening mode. So again, with the receiver, it's open reading pipe and radio.start listening. Whereas again, with the transmitter, it was open writing pipe and stop listening because you were transmitting, you weren't listening. Receiving commands. In the main loop, the radio.available function checks if there's any incoming data. If it is available, radio.read retrieves it and processes the command. So again, here we have radio.read receives and processes the commands. And again, radio.available checks if there's actually data available. That's akin to serial.available when we want to check to see if there's anything available via the serial monitor. If there's any user input, well, this similarly is checking to see if there's any input available via the radio. And then we use radio.read in the receiver code, just like we used radio.write in the transmitter code. So write in transmitting and read in receive. The parse command function breaks down the command into direction and distance, because you're going to pass a command like F space 50. So F is the direction, forward, and distance, the 50 would be the distance, which is then used to control the robot's motors. And then we have motor control. Depending on the received command, the robot will either move forward, backward, or turn left or right. And then the duration of the movement is calculated based on the distance provided in the command. So before I get into the differences between reading and writing pipe, let's go look at the code quickly. So again, these are just PDF printouts of the code, but they're identical to the code that would be in the Arduino. So if you look on the transmission code side, and the reason I have them up side by side like this is because the code is very similar in a lot of sense. There's only minor changes between them. So in both the transmission code and the receiving code, you have to include the RF24 header file. And again, it's in angle brackets because it's a built-in file. And again, I'm just going to have to scroll this down. Let's just make that a little bigger. So in both the transmission code here on the left and the receiving code on the right, we have the RF24 library. We have to define our CE pin and CSN pin, chips select pin, in both the receiver and the transmit code. Again, you can choose any pins for those. You'll notice I'm using different pins on the receiver side because pins 8 and 9 were taken up with my motor control. You set up the library, you create an instance of the RF24 library. By convention, we typically name it radio, and then use constructor initialization to pass in the CE pin as the first argument and CSN pin as the second argument. So again, you're creating an RF24 object for wireless communication. And you do the same thing in the receiving end. Again, you create the address in both the transmitter and the receiver code, and it's the same address. In this case, it's a one-dimensional array of type char, and it's constant because we're not going to be changing it. And so one-dimensional array of type character, or char depending how you like to pronounce it, is just a string. It's just a C-style string. And again, it's the same in both code. And then we've got a couple other things here. I'm just going to kind of go through and show at first the similarities between the code as far as the wireless transceiver, because that's the big thing about this coding challenge is the wireless capability. So then I've got an init radio function, which as the document comments show you here, it just initializes the modules for wireless communication. The mode is going to be transmission mode, TX, or reception mode. We're going to use transmission mode here on the left, and it's going to be set up for receiver mode on the right. And the address is just the address for communication. So maybe I'll just shrink that a little bit so we can see more. So if I go up to the init radio code for both of them, I just noticed something. I did make a change to the code, and I forgot to update it in this PDF, or I may not have even updated the code, I'm not sure. But I have the init radio code on the transceiver side takes in 3 parameter arguments, or correction, 2 parameter arguments. One is a string passed in by constant reference. The ampersand indicates the string is passed by reference, so not by value, which is the default. So we take in a string passed by constant reference, and that's given the parameter name mode, and then we pass in address, which is a pointer to a char, which again means a C-style string, and that's constant as well. And we use default initialization to initialize the default address if nothing is passed in. Okay, and the default address is this char one-dimensional array, or this C-style string. So when we don't pass anything in, it's going to be initialized to this address. So it takes those 2 parameters, and it's the same 2 parameters in both the transmitter side and the receiver side. The only difference is that in the receiver side, I've set up the first argument having a default argument passed in. So if I don't put anything in, it'll be in receive mode by default, which this is receive mode. I could have also done on this side, but I didn't. So that's fine. I also made this code void for some reason, so non-value returning, and I made the same function value returning on this side, Boolean, which I think was just doing this. I was making it that so that way this basically let me know if the radio initialized successfully. I really should have done that on both sides. I think that was an afterthought for me. I'm like, oh, you know what? I'm going to have this return a Boolean just to let me know that everything was successful. I think in this one I just use a serial print to indicate that it's successful. But not a big deal, just minor differences here. And both code basically start off the same. If not radio.begin. So basically, if the radio wasn't successfully initialized, I'm just going to output as much to the serial monitor. So radio initialization failed. And then I'm just going to halt the program and wait for it to be successful. So I'm going to use a while one loop, which is like a while true loop, which is an endless loop. And just I have a semicolon after it, so no body. So this just basically hangs out here and halts the program until, it just halts the program until this is successful. So I just stop the program, because if I didn't initialize, if the radio didn't initialize, none of the other code will work. So I just want to stop the program, therefore forcing the user to restart the Arduino. So just enter an endless loop. I do the same thing on this side. If radio.begin, if not radio.begin, output a message to the serial monitor indicating it, and then I return false. So this is the difference here. In this case, I just enter a while loop and just halt the progress of the program, forcing the user to restart their Arduino. Because if the radio never initialized, and the only purpose of this code is to transmit, well then I can't keep going on. The code doesn't work, so I just need to stop everything. Whereas here on the receiver code, I just return a Boolean, in this case false, indicating, hey, it didn't initialize, and then the code does something accordingly. And just so you know, radio.begin, this works very similar to serial.begin. A lot of the functions have begin, so this just returns a Boolean, true or false. True if it began successfully, false if it didn't. So therefore, if this returns false, well, not false is true, and I'll output this message. Then I'm going radio.setPA_level. In this case, this is just a constant associated with the library, rf24_PA_max. This could also be min. There's low, high, I think, are different constant variables. So we technically don't need max. I think I have it set at max just because, I don't mind the transceiver eating up some of my battery. It's actually it's one of its claims to fame is it actually uses low current. So I had it on max just so I'd have the best performance. But the distance that these the receiver and transmitter are apart doesn't require max at all. This could have been min. So I set up the PA level here as well, the power amplification level. And then something different I have in the receiver side is I have radio.set retries. So this is just configuring your retry settings. So basically, I want to try to hook up the radio and be successful. And these 2 arguments, this function basically does it. The first argument is associated with the number of milliseconds, or I believe microseconds, to wait in between a retry. It accepts arguments between 0 and 15, and each number is a multiple of 250 microseconds. And then the second argument is the number of retries. So I want to retry this 5 times. and a multiple of 250 microseconds, so 3 times 250 microseconds, I want to have a delay of 750 microseconds between retries, and I want to do a total of 5 retries. So that's that. I don't have that here in this setup because if I never initialize, there's no retry, I just halt the program and I make you restart. Then I have if mode equals tx, so if the user passed the first argument, the string tx, well, then I'm in transmit mode. Else, if mode equals rx, then I'm in receive mode. Else, well, I can only be in transmit or receive mode, so if there's an else, then I'm just going to put, hey, invalid mode, use tx or rx, and these are just escape characters, the backslash double quote. That just allows me to use double quotes inside string double quotes without affecting the code. I could have just used single quotes here and lost some of this ambiguity, but I like double quotes. And then I halt the program. So again, if you've entered an invalid command, you've tried to set it up not in transmit mode but receive mode, but instead you've tried to set up in some invalid mode, I just halt the program again and make you restart. Basically, if the radio doesn't start, I halt the program and make the user restart the Arduino. If they entered something invalid, you got to restart the Arduino. However, if you enter transmit mode, then I'm going to go radio.open writing pipe and pass in the address. And this, I'm just typecasting to const uint 8_t. This is just dereferencing. This is just for efficiency purposes. This could have been an int. This could have just been the address. This is just efficiency. But the important thing is because if I'm in transmit mode, I'm opening the writing pipe. And radio.stop listening, I'm stopping listening because I'm in transmit mode. So writing and stop. Whereas in the receiver code, if string compare, I'm just using, and I kind of do things differently between the two codes. There's no need for that. I just like to do it for education purposes to show there's multiple ways to do something. These code could have been identical for both the receiver and the transmit code could have been identical. I'm just doing different logic to accomplish the same thing. Here I'm going if mode equals tx because the quality operator works for this. Here I'm just using the string compare function. If string, which is kind of associated with C-style coding. If string compare function, the strcmp function here, which takes in 2 arguments, mode and the string literal tx, if that equals 0, that'll return a 0 if they're equal. Otherwise, it'll turn -1 or +1 if they're not equal, depending on which one comes first. But if they're equal, then I do this. Else if, I call the string compare function passing in mode and rx. If they're equal 0, I do this, set up for receive mode. Else, again, they've entered invalid command. I'm like, hey, invalid mode, use tx or rx. Here you'll notice I just use single quotes, so I didn't need an escape character. Whereas here, I need the escape character because I'm using double quotes. And again, then I return false. Because here, I just halt myself in an endless while loop when invalid command is entered, or when the radio doesn't begin. Here, if the radio doesn't begin, I return false, and return false if they enter an invalid command. Because again, I'm expecting a Boolean return type. Here I'm void, so I don't return anything. So just different ways to accomplish the same thing. Basically, this says, hey, what mode are you in? Transmit mode or receive mode? This says, are you in transmit mode or receive mode? If you're in receive mode for either of them, you're going to go radio.open reading pipe, passing in 2 arguments this time, not just 1 like it was for writing pipe. Writing pipe just took the address as a single argument. Reading pipe takes in 2 arguments. The first one is an integer from 0 to 5. And then the second one is the address, the same as writing pipe. These need to match. And then you're going to go radio.start listening. When you were transmitting, you were in writing pipe and stop listening. With receiving, you start listening and you're in reading pipe. And then I'm still putting a message to the serial monitor saying radio set to RX mode. That's just so I know that everything initialized properly, because I don't have a Boolean value returned. So this is the way that I know that everything got set up. I either say radio set to transmit mode or receive mode. That's my indication. Over here, same thing. If I'm in transmit mode, I'm opening writing pipe, passing in the single argument of address, and I stop listening, and then output a message to the serial monitor. If I'm in receive mode, I open reading pipe and pass in 2 arguments. The first one, again, is an integer between 0 and 5, and the second one is the address. The integer 0 to 5, that just indicates the pipe that you're receiving from. So when you're in transmit mode, you're typically just going to be transmitting data to one address at a time, one other module at a time. In receive mode, you can simultaneously listen to multiple different transmitters at the same time. So for that reason, you have to indicate what individual pipe you're reading from. And pipe 0 is kind of special because this one allows for automatic acknowledgement of payload. So if you're only listening to one thing, put 0 in there. But that's explained in greater detail in my other videos. So if you have questions, post them in the forum. Otherwise, I'd watch those other videos on where I go over the NRF24L01 Plus modules in greater detail, even than I am doing now, which as I'm looking and saying this, I realize that I'm already at 40 minutes in this video. So my videos aren't short. I'm not a YouTuber by any means. But if you're in receive mode, open reading pipe and then start listening, and then output a message to the serial monitor. The only other difference, and then that's the init radio code for the receiver. It ends there. It does that, and then it ends. For the for the transmitter, it ends. For the receiver, I have some additional code where I just flash an LED to indicate successful initialization. So the receiver code is on my robot car, and so I have an LED that just flashes 3 times. I use a for loop to iterate this code 3 times. I turn the LED pin high for 1/5 of a second, and then turn it low for 200 milliseconds, 1/5 of a second. I do that 3 times, just flashing the light on and off. And that's just a visual cue for myself to know, okay, it successfully initialized. And the reason I do that is because I'm untethered. I'm not hooked up to the computer, so I don't have the printouts that I'm using here only are effective if I'm hooked up to a computer. But when I'm not, I need the LED flash as my indicator. But again, I still do my serial printouts because they don't really add that much overhead. And when I'm hooked up, uploading the code and stuff, I like to know what's happening. So, and then on the transmitter side, I have this function called handle serial input. And so what that does is, well, as the Doxygen comment says, it handles user input via the serial monitor and sends commands wirelessly. On the receiver end, I have a bunch of different codes, but kind of the main one as far as receiving is to parse the command. So I'll talk about the transmit side first, and then I'll come back to the receiver side. So the handle serial input, basically, hey, if there's anything available on the serial monitor to read, if serial.available is greater than 0, then I'm going to read the string until the next line. So read the string till new line, assign that to the string variable command, and then I'm going to call the trim function using dot notation on command. So I'm going to call one of the string functions on the string variable command, and this just removes any white space or new line characters in case the user types some spaces in addition to their command. I don't want that. And then I'm going to go if radio.write, that passes in the arguments command.cstring, so I'm converting my string variable to cstring because that's what the write function expects. And then I'm going command.length. I'm calling the length function on my string because this write function expects the data, the C-style string that you want to send, and the number of bits that you want to send. So I'm accomplishing using this. And again, this is talked about in greater detail in my other videos. But again, that's what the write function does. And the write function, kind of a side effect of the write function, in addition to writing your command to to the radio to send wirelessly, it also returns a Boolean, true or false. True if it successfully sent the command, and false otherwise. So if this returns true, so if this is true, well, that means the command sent, and I'll output that message to the serial monitor. Hey, command sent plus command. I'll let you know the command that's sent. Else, if this returned false, that means I wasn't successful writing the command to the radio. So I'm going to go else, and I'm just going to send failed to send command. So that's the handle serial input. It basically, again, just takes the user input via the serial monitor and then sends the command wirelessly to the receiver side. And that's the setup, just basically does that. It sets up your serial communication, 9600 baud rate, and then while not serial, we just wait for the serial to initialize. That's all this does, because I really need this initialized before I start dealing with the radio. So that's all this does. I did it with this method where I put just a single semicolon inside the body of 2 curly braces inside the body. I don't need to do that. I could have just done the semicolon without the body. This was just overkill, I would say. And then I call the init radio function. So after the serial communication is set up, I'll get here and I'll call the init radio function passing in TX, so transmit. So I'm initializing the radios in transmit mode. And if you remember the init radio function, it takes in two parameters, the first one being the mode that you want, transmit or receive, and then the second being the address. But I set it up as a default argument, so if I didn't pass anything in, it would just default to the address that it needed to be right here. So that's what setup does. And then the loop is very simple. It simply constantly calls the handle serial input function. It just continually checks for serial input and then transmits the commands. So it just continually does this. Now over to the receiver side of things. So the receiver code, the one of importance, the big one here, is the parse command. It takes in a string command, and as you can read here in the document comment, it parses and processes the incoming commands from the transmitter. So, and the parameter that gets passed in is the command string received via the NRF24L01 plus module. So I get in that command that I received from the receiver, from the transmitter, and the command would be something like F, 50 or L, 100 for forward 50 or left 100. And then I initialize my two global variables. Bot direction, the direction I want to go, forward, back, left, right, and the distance. So the direction will be the first part of the command, the first character. So I'm going to go command.char@. So again, using dot notation and a function associated with string, which is char@, and you pass in an integer representing the index. Because remember, a string is really just a C-style, a string is really just a character array. This is a string, but it's really just a character one-dimensional array. So when I say char@, when I go command.char@0, I'm saying, hey, treat the string like an array and get me the first character, the character at index 0, which is first character. So it's going to return F or L, depending on which command got sent in. So that's the bot direction, will now be forward or left, let's say. And then I'm going to go command.substring2. When substring is an overloaded function, there's different versions depending on how many parameters you pass in. If you pass in a single parameter, it goes to that index location and grabs the substring from that index location till the end. So for 2, it'd be 0, 1, 2. It'll start at 50 and it'll grab the rest. So it'll grab the 5 and the 0. If I go here, 0, the comma is 1, and then the 1 is index 2, I'm going to grab 2 and everything that follows, so 100. So I'm going to go command.substring2.toInt. So I'm going to grab, the 50 and convert it to an int. I'm going to grab, don't mean that, the 100 and convert it to an int. That's what the toInt function does. So that'll now populate my bot direction and distance. And then I'm just going to output that to the serial monitor, bot direction plus comma distance. Now, if you're wondering where that bot direction and distance come from, they're global variables that are right here. String variable for bot direction and bot distance. And as per the comments, you can see it's just the direction that the robot will drive in, this change with direction, the two motors to go, and the distance to travel in each direction is distance. I skipped these earlier because I was going straight to the NRF 24L01 code, but really this is all the stuff. This is the original code associated with the original circuit for 5B, where it just has all your constants for the first motor and the second motor. Again, your two inputs, these are your direction control, and then your PWM pin is your speed control, and then you have your direction control for your second motor, direction control for your second motor, and your PWM pin for your speed control. Also have an int for my switch pin. This really should be a constant. I'm not sure if that's in the original code or if I accidentally took away the const, but this should be a constant. It doesn't really matter, but I'm not going to be changing switch pin in the code. It's always going to be on pin 2. In fact, I think I might have forgot to update this because I'm not actually using pin 2 now that I think about it. I had to hijack. No, I am using pin 2. My apologies. Sorry. And then the drive time and turn time. These actually do merit a little talking about because this is code associated with the original SparkFun challenge. And what this is, drive time is an int. And we'll just read the comment. Drive time, this is the number of milliseconds that it takes the robot to drive 1 inch. That just was determined when they wrote the code. It is set so that if you tell the robot to drive forward 25 units, the robot drives about 25 inches. I guess I got cut out here the thing. But if you tell the unit to drive 25 units, it'll drive about 25 inches. Because again, 1 inch is theoretically what they're assuming. This is the milliseconds it takes to drive 1 inch, 20 milliseconds. This might be different depending, you might have to change that. I didn't really change that because it wasn't the point of this coding challenge, but you would end up getting a ruler out or a tape measure or something and measuring this, and you might have to adjust this drive time accordingly, depending on your floor, the friction, all that sort of thing, your wheels, and change this so that whatever this time is, it relates to, it actually spins your wheel enough that you just move 1 inch. So you might have to increase or decrease this. The turn time has a similar functionality to it. This is the number of milliseconds that it takes to turn the robot about 1 degree. So it is set so that if you tell the robot to turn right 90 units, the robot turns about 90 degrees. Oh, here's the other comments here. They just got looped down. Here's the PDF. So back to where we were. That was parse command. I'll try to get a little quicker here. I'm always long in the wind, long in the tooth on these things. So toggle LED, this does the same thing as before, just toggles the state of the LED. So LED equals not LED. We're just toggling the state. If it was on, it becomes off. If it was off, it becomes on. And then we digitally write. We use the digital write function to write to the LED pin, high or low. And I'm using a ternary comment to do that. This is, again, just a succinct way to do things. I like ternary comments. If you've watched my previous videos, they're not as clear as like an if-else ladder or if-else statements, but I like the succinctness of them. They're just, all nice. So basically, digital write to the LED pin. If LED state is true, this is a statement that evaluates to true or false, and we know it does because it's a Boolean variable. So if this is true, we do what follows the question mark. We output high. We're going to write a high signal to the LED pin. If it's false, we're going to do whatever follows the colon. So we're going to write a low signal. Then we have this function, which is a callback for cloud command. Oh, I left this in here. Sorry, this is from previous code. This is, I have another video where I use the Arduino cloud to be able to control a remote control car that I created via wirelessly via my phone and the Arduino app. So that I meant to take that out, so you can just disregard this. Then I have on LED. So this code here actually is also associated. So both these codes are associated with the Arduino cloud and controlling the robot via a cell phone. But I don't do that in this video. If you're interested in that, search up on my playlist Arduino Cloud, and I'll show you how to control a remote control car or anything for that matter, an LED and different things via your cell phone and the Arduino Cloud, which is free. In the setup for this function, you'll notice I put this code. I'll just show this too. I have this little coding challenge document or comment here, just saying coding challenge, use NRF 24L0 plus 1 module to incorporate wireless comms. I included this here and up here as well. This just means that all this code was the original code. I might have modified the comment a little bit here, I think, but this is all the original code from the original circuit, and then everything between these comment blocks is code that I added for wireless communication. So all that was wireless communication. And then here in setup, this is all the original code, just calling the pin mode function, setting up your output pins for both your motors, and the switch pin as an input pull-up, so using that internal 20 kilo ohm resistor. And then the stuff that I added is between these two comment blocks. So I call the pin mode function for my LED pin that I added, setting that up as output. And then while not serial, so I'm waiting for the serial to initialize, the serial communication to initialize, which I just realized I should have had that obviously above here. I think I did change that in the code. I ended up printing off these things, and I think I made some minor changes. But that would just wait for serial communication to initialize. Again, apparently I'm calling the pin mode twice. Nothing wrong with that, it's just not necessary. So I guess I just didn't comment on all the code. But again, setting up that, really I want to make sure that that pin mode is set up, that LED pin is set up. I really want that LED. And then I'm calling my init radio function. So initialize the RF24 radio. So init radio function passing an RX, which it would have been by default anyway, because if I didn't pass that in, because I believe on this side I have a default argument of RX. So if I didn't pass it in, it still would have worked. But I'm being explicit here, which is good. And this returns a Boolean, remember, on this side. So this will return true if it was successfully started, false otherwise. So if it wasn't successful, well, not false is true, then I'm going to come in here and I'm just going to halt if the radio fails. Same as I halted on this side if the radio failed, because if it fails, I need to restart the program. The whole point of this is for radio communication. However, and then I set up the serial monitor and everything. If it doesn't fail, though, then I get past this spot, and then I do the things that I normally did. So again, I'm outside of this code block. This is all the code that I added to set up right here. And then this is all the original code as per the original circuit. Set up serial communication, 9600 baud rate, and then just prompt the user, hey, enter direction followed by distance. So the direction would be forward, backward, right turn, left turn, that sort of thing. And then a distance, like 50. So here's an example command, F50. And then in loop, I'm just going to make this bigger because we're done with the receive code. So let's just make this bigger. So in the loop, I'm going if digital read of switch pin equals low. So if the switch pin is low, active low. So if the switch has been turned on, then I'm going to check all the stuff. If it's not turned on, I'm not going to do anything. Else, if it's not turned on, I was doing a serial print high. That just was for debugging purposes. Outputting, hey, that I'm not low, I'm high, so the switch is off. But really, the code of importance is I'm going to call the right motor function, left motor function, and pass in 0, which means I'm turning them off. I'm turning the right and left motor off, meaning both motors are off, and nothing's moving. And then I'm doing a digital write of the switch pin to high. This was actually meant to be the LED pin. But again, I think I changed in the original code. A couple of mistakes here, that's fine. This should have been the LED pin. I just wanted to write the LED pin high so I could visually see on the car, okay, the LED's on. I was not successful in reading anything. Or correction, that the switch isn't on. Because sometimes on these switches, I don't know if it's on or off sort of thing. But really, at the end of the day, if the switch isn't on, the motor is off. That's the important there. But if the switch is on, and by on I mean low because it's an active low switch, then I'm just outputting a message to the serial monitor. That was just for debug purposes. But then I'm going to do all the stuff of the code. And again, just so you guys know what I mean when I say the switch is on, I'm going to show you the switch in case you forget. This is the switch I'm talking about. So again, if that switch is low, because it's an active low switch, because I'm using the internal, I don't have a physical resistor here, but I'm using the internal resistor associated with every digital pin. There's an internal 20 kilo ohm resistor. So it's being pulled high all the time through a resistor. It's a pull-up resistor. So if it's low, it means I've activated the switch. I've turned the motor on. So if the switch is enabled, then I'm going to come in here and again, between this coding challenge comment, this is all stuff that I added. I took out the stuff. Originally it was, hey, if the serial.available is greater than 0, because originally we just had this tethered to the computer, so I was just receiving communication via the serial monitor. Then I would read the string until space, get the baud direction, read the string until a space, get the distance, and then I would just print out those commands. But I'm not doing any serial monitor stuff. No, instead I'm receiving things via the radio. So very similar though, if serial's.available, it's if radio.available. So very similar, style. If serial.available, if radio.available. Right? So checking for wireless commands. If it's available, I'm creating a local variable, which is a C-style string. So a received data is a one-dimensional array of size 32 of type characters. So it's a character array and initialized to an empty string. So again, a character array is just a C-style string. And why 32? Because the write function is limited in that it can only transfer 32 bytes of data at a time. So this is the max string that we could receive at a time from the write function. So that's if I make my receive data string 32 in length, then I can receive the biggest string I could possibly receive from the write function anyway. And then I'm going to go radio.read. So again, I'm in the receive mode, so it's radio.read, which takes in, just like the write function, it actually takes in two parameters, the thing that I want to receive and the size of that thing. So again, I want to receive something and I want to assign it to receive data. I want to pass it by reference to receive data. That's what this ampersand does here. So it says, oh, I did that twice, didn't mean to do it. So it says whatever I read in, I want to assign it into my char one-dimensional array here, which I initialized times string. And then I need to know the size of what it is. So I just simply go size of this, 32 bits. That's the maximum thing I could receive. So again, in the write function, you'll remember that when we wrote a command, we passed in two parameters, a C-style string of the thing we wanted to transmit and the length. So it's very similar. Here we need to indicate where we wish to store this in the address of received data. So we want to store it in the address of received data. So we want to store it in this thing by reference, and we know the size of it, 32. And then again, what do we do with that command? We took all the time to get this command, we read it, we stored it in here. What do? Well, we call the parse command function, passing in that received data, but we typecast it to a string, calling the string function around it. And if you recall what parse command does, it is up here. And it simply takes that string and it grabs the first character, assigns it to bot direction variable, and then it takes the number, the integer, by converting to an int and assigns it to distance. So we basically get the direction and the distance from the command. So direction and distance from the command, and then we basically check and see what the direction was. So we have a bunch of if-else statements that basically just say, hey, if bot direction equals F, drive forward. If it's B, drive backwards. If it's R, do a right turn. If it's L, do a left turn. Those are the three things. I've added as part of the coding challenge, if bot direction equals T, I call the toggle LED method. Remember, that just turns the LED on if it was off, or off if it was on. It just toggles the LED. Yeah, so there you go. So if we're driving forward, we just call the right motor and left motor. We pass 200 to both. That's the speed. Again, you can pass in a value for PWM. This could have been a speed from 0, which is stopped, to 255 full speed. So 200 is, 4/5 of the way to full speed. So both motors have the same. That way they drive forward. And then I have a delay. The delay that I want to happen is drive time times distance dot toInt. And again, what is this representing? Well, again, this drives the motors long enough to travel the entered distance. Because again, the distance you're putting in, that's the distance you want to travel in inches. So if you type in 50, you want to travel 50 inches. So I have to take drive time and multiply it by that 50 inches. And where's that drive time coming from? Well, that comes up here. That is right here. Remember, the guys at SparkFun decided that 20 milliseconds, so 20, was the number of milliseconds that it takes this robot to drive 1 inch. So if I take drive times it by, if you want to drive 50 inches, so 20 times 50, it'll give me whatever number that is. I guess not 500, but 250, I guess. Jeez, I'm doing math. That might be completely wrong. I'm not sure. Let's see. 10 times 50 would be 500, so 20. Oh, it would be 1,000. Oh, I was horribly off. But I'm going to do an easier thing. If you want to drive 10 inches, you're going to take 20 times 10 and get 200. So 200 milliseconds of, if you have the motor on for 200 milliseconds, that should drive you 10 inches, according to the people at SparkFun. Again, you might have to adjust these numbers, because wherever they did this, where they decided 20 milliseconds drove them 1 inch, they might have been driving on whatever type of floor that worked, but your floor might have more friction, or the wheels might be different, the tolerances, your batteries might be lower, whatever. So you might have to adjust this number. But you're taking this drive times and timesing it by the distance, and theoretically your vehicle should move that distance. And turn time works similarly. So Yeah, that's how this delay works. You basically are turning the motors on at that speed for a certain amount of time that theoretically, if the drive time is calibrated correctly, will drive you that distance that you want to go. And then you shut the motors off. You drive that distance, shut the motors off. If they enter to B, you just do the same thing but in reverse. So you have negative speeds. That drives the motors backwards. But again, for the same drive time and the same distance. And then you shut the motors off. You're just driving backwards with negative speed. If they entered R for right turn, they want to turn right, well then you're going to drive the right motor, the direction they want to turn, you're going to drive that motor backwards and the other motor forward at full speed. So that'll give you a really quick turning radius. If you want to go right, well, if you make the right wheel go backwards and the left wheel go forward, you'll turn on a dime. Really good. And again, the same logic for the delay in all of them, and then you shut off the motor after you've done your turn or your forward or whatever direction you're going. If you wanted to go left, it's the same. It's the opposite of right. So you're going to have the right motor going full speed and the left motor going reverse at 200 speed. We already talked about this else. Basically, if the switch was never on from the start, we just shut off the motor. So we only ever did any of this logic if when we did a digital read of the switch pin, it was low, meaning if it was activated, because it's active low. And then we have the functions for right motor and left motor, which are, fairly just identical in opposite ways, if that makes any sense. But the right motor function takes in a single parameter of type int for the motor speed, and this is the function for driving the right motor. It doesn't return anything. Simply, if the motor speed is positive, greater than 0, then we're going to have our input 1 digitally write a high to input 1, and we're going to call the digital write function on input 2 low. So this logic is shown in the data sheet for the motor driver that we have. So all the documentation says if you drive input 1 high and input 2 low, okay, that will give you forward direction. If the motor speed that got passed in was negative, meaning you wanted to drive backwards, we write input 1 low and input 2 high. So the opposite of up here. That's for motor speed that is less than 0, negative speed, i.e. you want to go backwards. Else if they're both low, well then you just stop. This is stop when they're both low. Both high is an illegal state and don't do it. So this is all about this if-else statement, so this if-else ladder is all about direction. This is directional control, using digital writes to your input pins for direction control. Your speed control is done via analog write. So you do an analog write to your PWM pin for the particular motor. So PWM stands for pulse width modulation via analog write, and you pass in the motor speed. And again, we call the absolute value before we pass the motor speed into absolute value, so that way we don't get a signed number. We can't take negative numbers. PWM only allows for values between 0 and 255, so there's no negative numbers allowed. So if the speed that it got passed in was negative, which is valid because that's how you drive backwards, we just want to make sure that we're going at that speed, but we just needed positive. Left motor works, identically. If we get a positive motor speed passed in, we make the B channel input 1 high and the B channel input 2 low. If we have a negative speed, meaning we want to drive backwards, we do the opposite. Input 1 is low, input 2 is high, and if they're both low, we stop. And then this is all our direction control, and then our analog write is what does the speed control. So that's the code for my circuit. So I've got a lot of things happening here. I got the receiver code, and so the transmit code and the receiver code, and that's pretty much it. Before I do the live demo, I will quickly go back and finish reading this. So as you know, I kind of went through what we were doing, the introduction, the transmit receiver code, and then I didn't tell you the full explanation of the open writing pipe versus open reading pipe. But let's quickly go over those differences before the live demo. So and again, you'll notice blue is the transmit code and the pink here is the receive code. I just did that for a visual cue for myself as I was going through this. So with the open writing pipe, this takes one argument, the address, which is typically an array of bytes or a single integer. And this basically is when you're using this function when the module is set as a transmitter. So writing pipe, you're writing, so it's a transmitter. It specifies the destination address. So the address, the argument that takes in, is the destination address that you want to send data to. The argument that you pass into the writing pipe function is the address of the receiver. In the reading pipe function, it takes two arguments, not one. The first argument is the pipe number from 0 to 5. And the second argument is the address of the pipe. And the address matches the same address as the writing pipe function. So you use the open reading pipe function when the module is set up as a receiver. And why do we have the first argument? Why is there two arguments with the reading pipe and only one with the writing? Well, because that first argument, that pipe number, which is a number from 0 to 5, is because with the receiving mode, you can have multiple pipes can be opened for simultaneous listening. So you can be receiving from multiple sources at once, enabling the module to listen to multiple addresses. So that's why you need that first argument. The first argument is the pipe number. It identifies the logical pipe that you're listening for. Now, pipe 0, what we passed in, that's a special situation because if you use the number 0, pipe 0 is special because it allows for it allows you to automatically receive acknowledgement of payloads when data is transmitted, which is great when things are done automatically for you. The second argument specifies the address. So the pipe listens for the incoming data. So the second argument specifies the address. And again, that matches that of the writing pipe. Now, what's the reason for this difference? Well, again, as I said up here with the pipes, the receiver must be able to listen on multiple channels or pipes simultaneously, while the transmitter just typically sends data to only one destination at a time. So I kind of already talked about this, but what is the significance of 0 in the open reading pipe? That first argument. This is the primary pipe. It's the only one that supports automatic acknowledgement of payloads. So if you can use it, use it. So again, pipe 0 handles any responses from the device you are transmitting to. So if that device you're transmitting to has a response, pipe 0 handles it automatically. And this is crucial for bidirectional communication, which we're not using today, but I do have a video on that in my playlist. So again, you can just search for bidirectional communication with wireless communication NRF24L01 plus module, and I'll also include links in the video description. And then finally, I'm not sure if I really spent much time on this set retries, but the function radio.set retries, which I believe I have just in the receiving code, takes in two arguments. The first one delay and the second one count. And basically this whole function just configures your retransmission behavior, what your NRF24L0 plus 1 module does in order to retransmit code. So the delay, the first argument that gets passed in, is simply the time between retries. And again, the time is in multiples of 250 microseconds. So again, it accepts values from 0 to 15, which represent 0 to 4,000 microseconds. An example, like 3 in our case, I think we passed in 3, which corresponds to 3 times 250 microseconds, which means 750 microseconds. That's how long I want to wait between my retries. Obviously, the higher value increases the time that the module waits before retrying. So if you give 15, you're going to wait a lot longer before retrying a failed transmission. This obviously, increased time in between transmission retries slows down the code, but I mean, not by much. I mean, we're talking about microseconds, but it slows down the code, but it comes at the advantage of being more stable communication in noisy environments. So I only put 3 in mine, but I don't really have noisy environments and I haven't had any issues. But if I used a higher number, it would definitely be more stable, especially if you're noticing any issues in your own code. The second parameter is the count, and this specifies the number of retries that you want to attempt. Again, you can pass a number from 0 to 15. I think I used 5 in my example. But I mean, obviously, if you put a higher number like 15, you have a more shot of success and you won't get that, initialization failed. Again, I haven't had too many issues, so I kept it at 5, but it'd be no problem to up it. And finally, these are the key points of the code that I've talked about. Again, I've mostly focused on the NRF24L01 code because that's the main part of the coding challenge that I'm using. All the motor stuff, I basically just used the code provided from SparkFun, so that's not fun. My coding challenge was to make it wireless and not tethered because I didn't like the idea of walking around with a computer and a big long cord as I did this. Just seems something that my cat would play with. So the key points here are open writing pipe configures the transmitter's destination. So open writing pipe is on the transmitter code. Open reading pipe configures one or more listening addresses for the receiver. Pipe 0, that's special for acknowledgement payloads, and then the set retries function has two parameters, delay and count, which just determines how often and how many times the module retries sending data when transmission fails. So obviously the video is already quite long. It's like 115 minutes right now, so an hour and 15 minutes. But I'm just going to see what I haven't went through. Some troubleshooting that you might run into in this code in general. If the motor's not spinning, check the wiring of the motor driver. A lot of connections, easy to, mix up a connection, and just make sure that nothing's loose. One thing I've noticed in this circuitry course is wires constantly come loose, especially if you're jamming them around. That's often the problem. It's less coding, and I find more the circuitry. If the switch isn't working, again, make sure the middle pin and one side pin is what you're using for the switch. Don't use both side pins. What else? Jumper wires. This is the nemesis of a lot of things for me, with especially when I'm jamming things in a sandwich container, which I do in some of my videos if you've watched. Jumper wires, first of all, they go bad. They get bent too much. I do that often. They come loose. They're just a mess. So, especially the ones that come in this kit and a lot of the kits you get from like the Arduino kits online. So that's the troubleshooting. That's pretty much it. I'm just going to look and see what else there is. This is one of the videos I have on there. Again, it's a long video. It's an hour long. But this is one of the videos that I have showing communication. So I basically go through a couple of the different online tutorials. And I summarize them. I show various different communication methods. That's pretty much what I do, yeah. So I do that. So feel free to watch that at some time if you like. I go through again these tutorials in great details. So there's a lot of great tutorials out there for the NRF24L01 module. I mentioned them in my other video, but basically Autodesk Instructables has a good one. How to Mechatronics has a good one. There you go. And these are the key concepts. Again, these are gone. I go over this in great detail in the other videos, so I'm not going to go over it here. But yeah, there's lots of great information out there, and they're great little devices. So without further ado, let's do a quick live demo, because that's what we're here for, right? So I'll bring this up. So this might be hard. I don't have a second person here, but I'll try to. You know what? I'm going to put this down for a second. So let's just put this down for a second while I set things up. So I've got my transmitter code. And my receiver code. So my transmitter code and my receiver code. And we'll do a quick live demo. I guess I don't need the receiver code. So I was going to upload the receiver code, but it's already on the remote control car, so I'm not going to re-upload it. I'm just going to get this receiver code up. I'll just X that out, and I don't need this. So this is, so as you can see here, radio set to transmit mode, so it should be working. Now right now if I send a command, F,50, it failed to send, and there's a reason for that, because it failed to send because I'm actually going to try to just work something out right quick. I apologize you watching me do this here. I should have had this set up, but there you go. Okay, so it failed to transmit because I haven't set this up yet. So now I just plug this in. And I'm just going to move some things here. And we'll try to resend. And I can just also press the reset button on here. So again, radio set to transmit mode. So we're going to try to go F, 50. And it went about 50 inches. Now again, the point of this video isn't to show if the distance is correct, so I'm not sure if it is because I just used their numbers. It's to show the wireless communication. So again, if I press T, I'm going to press T in here and press enter, and you'll see the blue LED toggle on. I'm going to press T again and enter, and it shuts off. I'm going to press F, 50 and press enter. I'm going to press B for back, 50. Press enter. It actually hit this ledge here. So again, my daughter's having a sleepover downstairs on the hardwood, so I've had to, sequester myself to my bedroom, which is carpeted. So I put down this workout mat, but as you can see, when it slid backwards, it hit this ledge. So that didn't really work, but you can see it was going backwards, so the effect is still there. Perhaps actually I'll do it here just to show you. So again, we'll go forward by going F, 50. Ooh, really close. And now we're going to go B, 60. Close again. We're going to go F, 30. Just go a little forward. Oh, it wasn't showing you, but it did go forward. Now we're going to go right, 30. So right, 30. So we turned right. We're going to go left, 70. We're going to go back again. Back, 40. And we'll toggle the LED on again. So T, and then T again, and then F, 60. And that's pretty much it. So again, that all worked because the switch was on. If I turn the switch off, like I just did there, and I try entering commands, F, 50, you heard nothing happen. I'll do it again and show you the car. So F, 50. And when I press enter, nothing happens. You have to turn on the switch. And you'll notice that as soon as I turn on the switch, it continued with the command. So I'll put a fairly long command in just so you can see that happening. So F100, but the switch is off. Oh wait, no, I guess it wasn't. I forgot that it wasn't. So now I'm going to switch the switch off, and you'll see that it won't work when I put the command in. I'll do F150 or F200, a fairly long command, and I'll press it, nothing will happen, then I'll turn the switch on, and it'll start as soon as I get to it in time. Oh. Okay, so I shut off my phone. Okay. So, apologize, technical difficulties there. I didn't want this going off the carpet. But that's pretty much it. So, yeah, if the if you add these little modules to any of your projects, these NRF24L01 Plus modules, they add a lot of fun. And again, this you do need 2 of them. So again, I'm using an Arduino Nano here, and the only thing that's hooked up to it is this module. That's all that the purpose of this Nano is. But you do need a receiver and a transmitter, but you can do lots of cool things with them. So thanks for watching. If you have any questions, feel free to post them to the course forum. I'll be happy to answer them. Thanks for watching, and have a great night.